afternoon session. Our first speaker this afternoon will be Mikhail Cherdantsev from Cardiff University, and he'll talk on everywhere discontinuous anisotropy of thin periodic composite plates.
Okay, I would like to thank you for introduction. I would like to thank the organizers for organizing this nice conference and for giving me an opportunity to talk here. This work was done in collaboration with Mikhail Cherdantsev. He is also in the audience today. And this is about elastic composite plates. Composite structure is periodic. So first, this is the picture of a plate. We assume it is an elastic plate. It can be a sheet of metal or probably some rubber or plastic. And we can bend the plate, and we assume that the plate is thin. So the thickness of the plate is the small parameter h. Right, but this is a homogeneous plate, and these plates already were studied. I'll speak about this later. In our setting, we consider a periodic plate, so the periodic composite plate, and again we bend it. So the period of the composite structure is another small parameter epsilon. It also goes to 0 together with h, and we assume that epsilon is a function of h. So h is our main parameter, if you wish. So the interesting question: what happens in the limit when h and epsilon go to 0? Well, thickness of the plate disappears. So we end up with two-dimensional surface embedded in 3D space. And what is the effective description of elastic properties of such a plate in the limit? So this work is, well, the effect we get is the interplay of different asymptotic theories. So there is homogenization, which you have heard about already in this conference. We had a very nice introduction to homogenization by Valery Smyshlaev yesterday and by Tatiana Suslina this morning. So I don't need to explain much what is to-scale convergence now, because it was already introduced. So there are many different problems you can study in using homogenization. It is periodic problems or stochastic problems. Problems can be linear, which is a more usual setting for homogenization, but also there are nonlinear problems, in particular in nonlinear elasticity. There are many classical works on this subject. Also, the second asymptotic theory is linearization. If you again consider nonlinear elasticity, and you want to and you assume that the elastic energy is small, and you want to derive some linearized equations, so you use this linearization theory, right? So basically, I mean not the displacement, the gradient of displacement is small. Okay, and another thing is dimension reduction. It's a study of various structures which are thin walls or probably rods. It can be periodic or non-periodic. So examples are flattened graphs, for instance, and when the size of this flattened graph goes to 0, you end up with one-dimensional graph. So, or you can study membranes or plates, as like here. Now, if you consider a setting which allows, which includes homogenization and linearization together, the example of this is periodic nonlinear elasticity in small energy displacement regime. You can consider homogenization and dimension reduction problems. It's periodic thin structures with with thin walls, for instance, periodic membranes, and you can consider problems involving linearization and dimension reduction, and this is exactly the homogeneous case corresponding to the current work, elastic plates and bending regime. And if you have all three effects together, we talk about our problem today, periodic elastic plates. So you can see the increasing difficulty of the theory you end up with. Now, this is, so I first would like you to introduce with the standard setting of nonlinear elasticity. So in variational formulation, in variational formulation of nonlinear elasticity, we consider a functional which includes this nonlinear term plus some linear term which involves boundary conditions and force term. Right. So what is this nonlinear term? Omega here is a reference domain, the shape of the elastic body before we applied any deformation to it. Now u, this function u here, is the deformation of this elastic body. So u of omega is the shape of the body after the deformation. Now w is the elastic energy density function or stored energy function. So at each point it gives you a density of elastic energy which depends on the amount on the strain, right? So on the gradient of deformation. Basically, gradient of deformation represents the amount of deformation at every particular point of the body. If u of x is identical deformation, then if you have identical deformation, then the natural physical assumption on the stored energy function that the energy, elastic energy, is zero on identity matrix. Another natural physical assumption is that this stored energy function is frame indifferent. So f here represents basically the gradient of deformation. Now, if we apply the deformation to the body, we have f gradient u, and then we make a rigid rotation. We end up with r times f, but the energy, elastic energy, should be the same. So this is the frame indifference. Another natural assumption is that, quite natural, is that the stored energy function is bounded by from below by distance squared from the gradient of deformation to the group of rotation, to the group of rigid body motions, right? So this assumption naturally appears if you assume that the stored energy function is smooth enough with respect to f. So you can write Taylor's expansion near its minimum. So the function w takes its minimum on identical matrix, which is 0, and on all rotations as well. So if you write a Taylor expansion, first term is 0, second term is also 0 because it's a minimum. So you have only a second term which is quadratic. So this is why this assumption is quite natural. Now we assume indeed that the stored energy function is smooth enough so that you can write the Taylor's expansion in the vicinity of identity matrix. So if basically the gradient of deformation is close to identity matrix. So this G represents the small gradient of displacement, and you can expand your stored energy function in this way. Okay, so now I would like to talk about why this topic of elastic plates and other structures like rods, shells is important. I'm quoting here a couple of lines from a paper by Friesike and Jameson Muller, who actually started this rigorous study of on elastic plates, offering method which allows to derive some limit plate theories, rigorously starting from three-dimensional nonlinear elasticity. So in their paper in 2006, they say that fundamental problem in nonlinear elasticity is understanding the relation between the three-dimensional theory and theories for lower-dimensional objects, such as plates, shells and rods, etc. And when they wrote this paper, actually when they wrote the first paper, which was in 2002, there were many such theories which were heuristically derived, and they were quite inconsistent. So they say that the derivation and validity of such theories has been the subject of many discussions. Okay, so they start from a nonlinear elasticity setting. They consider homogeneous elastic plate. So there is no dependence on x variable of the stored energy function. So it is the same in every point of the body. Now, they have two big papers in 2002 and 2006 considering such a problem, and omega h here it represents the plate that I gave picture for. So it is two-dimensional domain omega times h times unit interval I. Okay, and the limit theory that you get depends on the energy scaling for this functional. Right? So if you consider this functional and plug in, and you have a sequence of deformations, we can say UH, such that on this sequence of deformations, the energy is of order h, then in the limit you get membrane. So it's membrane behavior. Basically, membrane is allowed to be stretched. So stretch gives you a displacement of order 1. So it means that the density of elastic energy should be of order 1 as well. And when you integrate over this domain, which volume is of order h, you end up with this energy scaling. Now, if you go to lower energies, things become more difficult to explain why these energy levels give you certain regimes. But this is the theory for this is this theory that they developed, right? So we have energy scaling of order h cubed, which means that the density of the energy is of order h squared. Then you end up with a bending plate which agrees with the original Kirchhoff ansatz for bending plates. If you have energy of order h to the power 5, so the W is of order h to the power 4 in this case, you end up with von Karman linearized plate theory. Okay, and again I'll quote several lines from different works. So Truesdell in 77 says about von Karman's theory, which these guys rigorously get in this regime, that analysts seem to love it, and it makes no sense to critical students of mechanics. Now, Elijah in 87 refers to the von Karman theory as a typical example of a bad theory. And again, I'll quote Friesike, James, and Müller on their bending plate. It's from their work from 2002. The limit energy agrees with exponential expression proposed in the original work of Kirchhoff. So they talk about this energy scaling, this energy regime. Well, it was proposed by that time, 150 years ago, but not with the expression obtained by suppressing the geometric nonlinearity, which much of the subsequent literature has associated with Kirchhoff's name. Likewise, it does not agree, their theory, with the expression obtained via a standard nonlinear Kossera ansatz, sometimes called the nonlinear Kirchhoff-Love ansatz in the literature, even though it's not due to Kirchhoff, for the three-dimensional deformation. So it shows us how important this study is and how controversial heuristic plate theories were by that time. Now, what about the result of Friesike, James, and Müller relevant to the current work? So we consider the bending regime, so the energy scaling of h to the power 3. So I'll just explain what they get in this regime for homogeneous plate. So we can rescale the functional. So basically we rescale the transverse variable x3 by multiplying by h to the power -1, so that it belongs to the interval I. So omega is the rescale domain. We have to rescale the third differentiation with respect to the third variable as well. So that's why we put index h next to the gradient. So bending energy becomes h to the power 2, and if we divide the, if we have a sequence, well, if we consider this functional, rescale functional by h to the power 2, and pass to the limit, the correct limit functional, which describes the plate behavior, is this one. It's given as an integral over two-dimensional domain omega of a certain quadratic form of the matrix of the second fundamental form of the limit surface U. So what happens is the deformations which give you energy of order h squared, they in the limit converge to a two-dimensional surface embedded in R3, which is isometric. So well, example of an isometric surface is a sheet of paper. If you bend it like this, it will give you this isometric surface. You're not allowed to make like bend it sharply, like making corners. So as soon as you, as far as you bending it without these sharp corners, you get isometric surface. It doesn't allow stretch or compression in plane directions. Okay, so this is the definition of the second fundamental form. Basically, it consists of one of a curvature of one of the principal curvatures, which is non-zero. So basically, two principal curvatures of this of an isometric surface is such that one of the curvatures is always 0 in every point, and another is well, non-zero if it's not flat, the surface. So it consists of this non-zero curvature times some matrix which obtained, which indicates the direction of the bending. Okay, so N here is the normal, unit normal to the surface. Now, what are the key elements of their proof? And so this is the most important element of technical element, which allows to rigorously pass to the limit in such when you linearize from nonlinear elasticity to linear elasticity. This is rigidity estimate. So it tells you basically that if the elastic energy density is of order if it is small, then this distance to the group of rotations from distance from the gradient of deformation to the group of rotations is small, because we have this assumption here, right? So if density is small, this distance is small. But then if distance is small, the distance from the gradient to a single constant rotation matrix for some rotation matrix R is also small, and this constant C depends only on the shape of the domain D. You can actually scale the domain uniformly, and you'll have the same constant. So it allows to split the omega h into small cubes of size h. On each cube, you approximate the gradient of deformation with some rotation. So basically, it gives you the on the whole set little omega. It gives you a piecewise constant function with values and groups of rotation, which approximates the gradients of the actual deformation in every point. Well, in terms of L2 norm, obviously. So, and also it allows to conclude that the difference between values of this piecewise constant function is small, is of order h, if we make a little step from one h cube to another h cube, to a neighboring h cube. And then having this in hands, you can argue that the gradient converges strongly in L2 to the this structure. This is the gradient of the limit surface, isometric surface. It depends only on two variables, x1 and x2, which denoted by x prime. Hence, we have the gradient prime here. So it is only with respect to x1, x2 variables. And n is the normal to the surface. And in fact, the surface is it's an additional piece of information that they get, that surface is actually twice differentiable, and is isometric. Now, okay, our setting. Basically, it is very similar, with the only exception that we assume this dependence on x prime variable, on in-plane variables, and the dependence is periodic. So W of y is comma f is periodic with respect to y, and the unit square is the cell of periodicity, and we assume that period is small by dividing by epsilon here. Again, we rescale the functional in the same way. So now the transverse variable belongs to the unit interval rather than a small interval hi, and we rescale the third derivative with respect to x3. And again, we consider this energy, this energy regime for the h squared. Okay. This in this area, the work was done before us. Some work was done before us. So basically, you can consider different regimes depending what is the relation between epsilon and h. So if these three guys, Honung, Neukom, and Velcic, in 2012, they published a paper considering these two regimes when epsilon is for the h and epsilon is much smaller than h. So the period either of the order of thickness or less than the thickness, much less. Okay, so in the end, they have in the limit they obtain a elastic functional, which also which is very similar to in the form obtained by Friesicher, James, and Müller. So it is a quadratic form. The difference is that this quadratic form is different from the quadratic form those guys, Friesicher, James, Müller get. So For this this particular scaling, when epsilon is of order h, this functional, this quadratic form is defined as a minimum infimum of this expression. So Q3 is that quadratic form from the Taylor's expansion of W. It obviously depends on y, as W depends on y. And you relax this with B and the gradient of this test function phi. So basically this is a relaxation, sort of relaxation technique. Now, if you consider this regime, the answer is slightly different. Now, instead of the derivative with respect to third variable of phi, you have an independent function d. Okay, now when we were finishing our problem, Velchich in 2014, last year, he published a paper, well, on arXiv, I think. I'm not sure if it's published in a journal, considering the regime which we also consider in this work. So h is between epsilon and epsilon squared, right? So the period is much larger than the thickness of the plate. And he also assumed dependence on stored energy function on the transverse variable x3. And this is his formula. So basically he's got the same functional with the quadratic form, which is given by this formula. Now he has to take relax also with respect to x3, third variable x3. And he's got a more complicated expression here, but notably he's got this second gradient of a test function which appears in our work. I will speak about this a bit later as well. Now, what is new in our work? We also basically, I have to mention, we also consider the regime when h is much smaller than epsilon squared, and which is most interesting.
Much smaller than epsilon. Oh, sorry. Yeah, sorry.
H is much smaller than epsilon squared.
Sorry.
So the period is basically the periodic cell behaves like sort of a plate in itself, miniature plate.
So our regime is different to what you are pointing at now.
Yeah, our regime is different. Yeah. So, but what is new in our approach is that we introduce the modified mid-surface of the plate, and we got actually boundedness of its second gradient, which is quite remarkable because from the outside the sequence of deformations is from the space H1, only one time differentiable. So we only know about the boundedness of its first gradient, and even if you apply modification to some function from H1, you get infinitely differentiable functions, but you don't have any control on high derivatives. So, for instance, second derivative, you don't have any control on this normally. But in this case, in the case of the plates, we get the boundedness of the second gradient of this modified surface. Now, then we prove the two-scale convergence of the second gradients. Well, it is more or less follows the standard lines of standard proofs of two-scale convergence for the first gradient, but still it's a new thing. We get isometric constraint on the microscale for this supercritical regime, which is a very interesting feature, which gives you actually, which is due to which my talk is named everywhere discontinuous anisotropy. It gives you discontinuous anisotropy, this isometric constraint on the microscale. And well, it's a technical bit. We regularize limit isometric surfaces with respect to the bending directions, it is important because the magnitude of the energy, elastic energy, depends on the direction of bending. This is why we had to make sure that our directions give us quite regular set to construct a recovery sequence, which sort of imitates the minimize of the original problem. Right. So now our result in this regime, when h is between epsilon and epsilon squared, so it is small but not super small compared to the period of the structure. Again, we obtain the functional of the same form. The only difference in this quadratic form Q, which we call Q form, and it is defined as a minimizer of this expression. So we minimize with respect to functions psi, which are 2 times differentiable and periodic on the with respect to variable y on the unit square. And this formula is quite simple compared to the formulas of our predecessors. Now, you see here this second gradient appears is exactly to this technique, modification technique, and the existence of the second gradient for the modified surface. Okay, and the Q2 here is just obtained by dimension reduction from the form Q3, which is in the Taylor's expansion of stored energy function W. Okay, if we can compare our results to what Velchich has obtained in this regime. So if we remove x3 dependence from his setting, we can actually drop that one of the functions with respect to which we relax the problem. So we drop d, which corresponds to x3 relaxation. Now, basically, the problem, this homogeneized quadratic form now is given by the minimization of this problem, and if you integrate with respect to x3, you see that basically the main point here is that this function q to v depends on the second fundamental form, and we minimize with respect with all other functions, and this bit is non-negative. So if you take b and zeta equal to 0, then it just disappears. So we end up with our formula. Okay, what is key elements of the proof? This is the probably one of the most important ingredients of this work. So introduction of this modified mid-surface of the plate. So we integrate with respect to transverse variable x3, so that we end up with a 2-dimensional surface rather than a 3-dimensional plate. But also we modify the result by a standard modifier, is support h. So basically, it is more this mid-surface is modified on the scales much smaller than the periodicity of the structure. So in this way, we make sure that oscillations related to epsilon scale, we keep the information about these oscillations of the deformation in this modifier as well. Now, we can prove that the second gradient of the modified surface is bounded in O2. And this is due to the fact that, using the same approach as Fritzsche James Müller used, we see that the gradient of the deformation can be approximated by this piecewise constant function in the group of rotations, and the order of approximation is of order h. And also, as I already mentioned, if we shift from one point, from one h cube to a neighboring h cube, this difference will be of order h. Basically, it means that we can, putting this together, we can consider finite difference like this, and it is bounded. Well, we do it, we prove it rigorously. So basically, passing to the limit as h goes to 0. Well, we don't need to pass to the limit, but we can prove rigorously that this implies the boundedness of the second gradient, right? And by the way, if the second gradient is bounded, we know that the sequence of deformations converge strongly. A sequence of mid surfaces converge strongly to the limit isometric surface U in the norm of H1. And this result is obtained much simpler than original result by Friesike, James, and Müller in the 2002 work, due to this approach of modified mid-surfaces. Now, then we need to consider the second gradient. But by the way, why second gradient is so important? Because if you look at the second fundamental form, the matrix of the second fundamental form, it is given by the gradient of U transposed. This is a 2 by, well, this is 2 by 3 matrix, or 3 by 2 matrix, right? When we transpose, it becomes 2 by 3. Now multiply by the gradient of the norm to the surface. So the result is 2 by 2 matrix. And but what is the norm? Norm is the vector product of the first derivatives of the surface. These are unit vectors which are orthogonal to each other and tangent to the surface. So if you plug it here, effectively you get second derivatives of U. This is why considering the second gradient is very important. We need to understand its limit, and because I want to say something about the behavior of this of the limit on the micro scale, we pass to the limit in the two-scale convergence setting, in the sense of two-scale convergence. And two-scale convergence was very nicely introduced yesterday by Valery Smyshlaev, so I don't want to repeat all the introduction. I don't have enough time, unfortunately, for this. So the limit is the, and it's only Victor scale limit, so this Victor scale limit is the second gradient of the limit surface plus the second gradient with respect to y variable, which corresponds to the this periodicity, periodic structure of some other function phi. And if you consider, well, by the way, here is a typo. We need to multiply this whole thing by h3. So this thing converges to that structure, familiar structure. So it must be R H transposed grad H U H minus identity matrix over H converges to scale. Well, I slightly cheated here also I didn't include another term which is independent. So this term that is there, it also includes this factor x3. Right, but there is another term which does not depend on x3, and basically when you pass to the limit and use well, you can write an inequality where this second term disappears, and it is actually not important. This is why I didn't include it. Now, why, by the way, we consider such structure? Because due to frame indifference, we can take our gradient of deformation, plug it into the stored energy function W. It equals to this. So we can multiply by this function RH, which is a rotation matrix. And then, if we can write it this term in the form, because we know that grad HU is close to RH, the whole thing is close to identity matrix. So we end up with identity matrix plus H times this term. So RH transposed grad HUH minus identity matrix over H. And then we can apply Taylor's expansion, so that it will be H squared times quadratic form Q3 from the Taylor's expansion times this term here plus small order terms. This is the idea why we consider this structure, and it gives us in the the limit problem, the argument in the limit problem. And this function psi is just this limit phi multiplied by scalar product by the norm to the surface. Okay, and phi is periodic, and phi and psi periodic with respect to y. So we can show passing to the limit and then writing the inequalities. We can show low bound inequality. So in the limit, on this sequence of deformations, the value of the limit energy on the limit surface U is not greater than this lim inf, right? So this tells us that this functional is a lower bound, sort of a limit lower bound for this functional. Okay. What about what if it's too small? Is it exact lower bound? So all these things make sense only if we can show that it is exact lower bound. And for this, we need to prove that for any limit surface, we can construct a recovery sequence of deformations on which energies EH converge to the energy E home. For simplicity, if we start from the homogeneous ansatz, basically this thing represents the recovery sequence for homogeneous case. You have a limit surface, you flatten this limit surface, so you have hx3 times the norm. So so you get a thin plate of size h, and this is another term which enters the relaxation formula, which gives you Q dimension reduction. Okay, if you consider the gradient and you multiply it by a rotation matrix transposed, keeping in mind that we're looking for such calculations, and we plug it into the formula, we can show that using the Taylor's expression that this is this is the main term is the quadratic form Q3 on there must be u here, gradient of u, on this structure, and you can pass to the inequality showing with quadratic form Q2. But actually, if you choose D suitable D, there will be exact equality here. So D should be a minimizer of certain problem in dimension reduction. Okay. So in our case, it's somewhat similar. We want to construct a recovery sequence such that it converges. So we take some isometric, two-dimensional isometric surface. We want to construct a sequence of deformations which converge to U strongly in each one. Okay, it's not very rigorous here because it's defined on space of 3 variables, and this one is only on 2 variables. But in a sense, we can make it rigorous. Now that the limit of scaled energies on this recovery sequence converge to the elastic energy corresponding to the isometric surface. Okay, so basically, if you compare to the ansatz that is used in here in homogeneous case, you see that we have used the same. This term came from there, and this term came from there. But now we have these 3 extra terms which involve this expression from the limits, quadratic second gradient of character phi. So we plug them here, where phi basically in this formula is the minimizer, or almost minimizer, of this problem, which gives you a homogenized matrix. So we plug them here, here, and here in such a manner that once you consider this, this expression for such an ansatz, you end up in the limit with this expression here, with no extra terms actually. Well, there are extra terms, but then you depending on D, but then you relax with respect to them. Now, and we can prove that indeed for this sequence, this convergence is true. It means that E hom is the exact lower bound. So the energies are attained by the energies of the original functional. Okay, so it is a proper variational limit. By the way, well, I've already mentioned it, that this approach is called gamma convergence of nonlinear functionals, introduced by D. Georgi quite a while ago, and very popular in nonlinear community. Right, but what is the story over? This is actually true. This result is true only when h is not very small. So it is less than epsilon, greater than epsilon squared. But what happens in the case when h is extremely small, supercritical regime we call it. So actually the regime when h is of order epsilon squared, we call it critical regime because there is a transition from one behavior to another behavior in the limit problem. And it's still an open question, an open problem. But we managed to get a result for this regime when h is very small. So again, if you consider that ansatz, which gives us the recovery sequence.
So h very small means epsilon to some power with.
Yeah. Well, basically, h is little o of epsilon squared. This is what it means. And it can be anything. It can be a power. It can be multiplied by logarithm. Right. So if you consider this and consider this expression, which appears here again, I remind you. So this is the most important expression in the linearization procedure. We see that we can see that after differentiation and substitution, we get an error of order epsilon squared. It's okay when h is epsilon squared is smaller than h. right? So the areas of will be of the order smaller than the main term. But if in this case it's not true. It's not true when when h is of order epsilon squared. The error is not an error anymore. It's a main term of the same order term as the first one. And if h is much smaller than epsilon squared, this is the main order term. So something goes wrong here. The error is too bad, and this is because the surface, basically in this ansatz, this is the surface, and this is the flattening, making it a plate in this bit as well. So this surface is not enough isometric, and we need to produce something more isometric, like giving a much smaller error. And basically this error must be of infinitely small order, because we consider all possible regimes when h can be any order smaller than epsilon squared. So I need to go a bit faster. Eventually we found out that if you want to produce such a surface, is isometric surface, basically we try to approach the construction of such a surface using formal asymptotic expansion in powers of epsilon and h, when we wrote several equations for first several orders of h and epsilon. We found that the solvability condition on these equations are equivalent to this isometric this constraint, which we call isometric constraint. But it was only for formal approach, so we and it was not possible to prove, I think, it by asymptotic expansion approach, right? So we had to prove this. We managed to prove this passing to the limit. So basically we again started from used to scale convergence here, passed to the limit rigorously to obtain this constraint exactly in this regime when h is smaller than epsilon squared, right? So the right homogenized functional in this supercritical regime is the same as previously, but the minimization we minimize here over these functions psi, right? But also this functions psi has to satisfy this isometric constraint. And depending on the orientation of the axis of the bending with respect to the periodicity structure, we can have directions which are irrational or rational. In irrational directions, we cannot find if the direction is irrational. This constraint tells you that actually function psi depends only on one variable which goes along the direction of the bending, and we cannot find for rational directions any function different from zero, well, or constant, any function different from constant which is periodic on the cell. So in fact, if the direction of the bending, which is encoded in this second fundamental form, if the direction is irrational, this term disappears from the formula, and we just integrate this with respect to y. This is so there is no corrector for homogenized quadratic form. But if it is rational, then we can find there exist in general there exists functions which are periodic on the periodic cell, and satisfy this condition, isometric condition. So we have everywhere discontinuous anisotropy, and this is exactly due to this constraint here. So it means in irrational directions it is harder to bend. In rational directions it is easier to bend, because we minimize this in rational directions with respect to phi. Okay. Okay, I'll just skip it. Probably I quickly just show last 3 slides. Main points of the proof. So basically we started from considering this determinant of the second gradient of the modified surface. This is right identity, and if we pass to the limit in the left-hand side, we can show by compensated compactness theorem that it is weak to scale converges to this expression depending on the limit surface U, right? And if we look at the right-hand side, we can formally write it like this. You can say it's rubbish. How can you differentiate so small things? But in fact, we just need to multiply this by a test function and integrate by parts twice. So all these derivatives are applied to function eta now, and pass to the limit. Then the whole thing disappears. So we see that the limit of the weak star limit of the right-hand side is 0. Hence, we conclude that this expression here is 0, the left-hand side, the expression that we get on the left-hand side. And then from this follows that this isometric constraint, because the second gradient of u and second gradient of phi with respect to y are related to these things here. Okay, and this is some analysis for this is some analysis for isometric plates, but and I don't have time for it. And eventually we construct an isometric surface which is give us recovery deformations using the tangent vector to the isometric surface. So, and it is exactly isometric. Okay, and this is almost everything I wanted to say. I have a small, a bit complicated device showing a plate. So basically, it illustrates you that you can bend a plate which is isometric. I mean, if you bend it like this, then the micro oscillations, which represented by function psi, can go along the bending. If you try to bend it across, it doesn't bend because isometry gives you this isometry is violated in this regime. So this illustrates you that micro oscillations corresponding to psi can go only along the bending of the plate in this regime. Okay, thank you very much.
You could have made this thing two-dimensional, right, waves?
Yeah.
And you could demonstrate rational versus irrational, right?
Well, yeah. It's a
You could not make it from a plate sheet, right? But if it had this periodic structures, right? Some humps periodically, then you can bend them.
Yeah. I think it's not that difficult to produce in an engineering laboratory. Device showing the effect of smooth, soft and stiff bending depending on the direction.
What do you expect in the critical regime?
In the critical regime, I expect that this isometric constraint should be valid. The problem is that if you use the same approach as here, and you consider arbitrary deformation which gives you energy of order h squared, it doesn't have to be relaxed in the sense of when you pass to the limit, relaxed with respect to homogenization stuff. So it will always give you an error of the same order as the main term, but the energy, the total energy, will still be h squared. There is no contradiction. So, but if you want to get isometric constraint in this regime, you have to consider almost minimizers. Almost minimizers will include that relaxation terms, and they will not produce such a big error. But it's an open question, and maybe next thing I'll do.
You gave some overview, then your own work. There are a bunch of various regimes when you have h, small epsilon.
Do you want me to show it to you?
Yes, but I think is it always assumed that the periodicity, right, in epsilon
Yes.
is only in X prime, right? Or is it not an issue if there was also periodicity across in this
Well,
eventually vanishing
it's
in X3, I mean, right? Which eventually.
but then the periodicity has to be one of another smaller than h. So probably you can consider something like this, but
Not in the regimes which you are considering.
no, and I believe it will be much harder if you look at what Igor Velchich obtained in this with the dependence on transverse variable. This formula is much more complicated now. If you include periodicity and small parameter there, I don't know what would appear here. It could be just ridiculously complicated.
Thank the speaker again.